On October 29, 2025, at precisely 11:27 Universal Time, something passed within 1.36 astronomical units of our Sun and emerged transformed. Not vaporized like Comet Lovejoy, not shattered like Ison, but changed, as if the star's corona had whispered instructions to something ancient, something that remembered how to listen. What transpired in those 4 minutes of solar fire may fundamentally rewrite our understanding of what travels between the stars. It challenges not just our models of cometary physics, but our deepest assumptions about whether we're truly alone in cataloging the cosmos or whether something else has been watching, measuring moving through the void far longer than we've existed to wonder. 3 independent space agencies, NASA's Jet Propulsion Laboratory, the European Space Agency's Solar Orbiter, and ground-based observatories across 4 continents, recorded the same impossible sequence. An object that should have behaved like frozen rock and ancient ice instead displayed characteristics we associate with engineered materials, perfect thermal regulation, specular reflection, electromagnetic coupling with solar activity, and most unsettling of all, a trajectory that adjusted itself precisely when the Sun released its most powerful flare in months. But here's what transformed mere curiosity into existential unease among astronomers worldwide. The anomaly didn't occur randomly. It happened exactly when AR 3510, a massive sunspot complex, erupted with explosive force. And in those moments, something 100 meters across, traveling at 200,000 kilometers per hour, responded as if the Sun had called its name. Tonight, we follow the trajectory of 3I Atlas, humanity's 3rd confirmed interstellar visitor. From its discovery in the cold reaches beyond Neptune to its inexplicable behavior near our star, we'll explore why its passage has forced even the most skeptical scientists to ask a question that once belonged only to philosophy and speculation. Are we merely observing the universe, or has something been observing us in return, leaving evidence we're only now learning to recognize? This isn't speculation dressed as science. Every anomaly we'll discuss tonight comes from peer-reviewed data, published observations, and measurements so precise they've revealed contradictions no natural model can reconcile. The mystery of 3I Atlas isn't what we imagined, it's what we measured, and those measurements refuse to behave like anything in our catalogs. So settle in, dim the lights, and prepare to follow an object that traveled for millions of years through absolute darkness, only to perform a 4-minute dance with our Sun that has left astrophysics itself questioning the boundaries between the natural and the impossible. On the first day of July 2025, the Atlas telescope system on Mauna Loa, Hawaii, detected a faint point of light moving against the background stars. It was unremarkable at first, a smudge of reflected sunlight, barely distinguishable from the thousands of asteroids that populate the solar system's outer reaches. But within hours, as additional observations poured in from telescopes worldwide, something extraordinary became clear. This object wasn't bound to our Sun. The mathematics told the story with elegant certainty. Its orbital eccentricity measured 6.137, far exceeding the value of 1.0 that separates elliptical orbits from hyperbolic escape trajectories. This wasn't a piece of our solar system's ancient debris. It was an interloper arriving from interstellar space itself, the 3rd such visitor we've ever confirmed. The first, Oumuamua, stunned the world in 2017 with its elongated shape and inexplicable acceleration. The second comet 2I Borisov arrived in 2019, behaving more like the comets we understood, outgassing volatiles, sporting a visible coma following predictable thermophysical models. When 3I Atlas appeared, astronomers hoped it might finally provide a clear template for understanding these cosmic wanderers. Instead, it would become more puzzling than both predecessors combined. What makes an object interstellar isn't merely its origin beyond our Sun's gravitational domain. It's the signature encoded in its motion, a hyperbolic trajectory that screams of speeds and vectors incompatible with solar capture. 3I Atlas approached from the direction of the constellation Ursa Major, moving at 48 kilometers per second relative to our sun, carrying with it the momentum of its journey through the galactic disk. To achieve such velocity naturally, it must have been accelerated by gravitational interactions with other stars slingshot across parsecs of void, traveling for time frames that dwarf human civilization. Ancient cultures watched the skies with religious intensity, interpreting comets and unusual celestial visitors as omens, messages from the gods. The Maya developed astronomical tables of extraordinary precision, tracking Venus's movements to within minutes over centuries. They called these wanderers the bearers of knowledge, celestial messengers whose appearances coincided with earthly transformations. The Babylonians recorded hairy stars that defied the orderly procession of planets, treating them as harbingers of change. Were they witnessing interstellar visitors like 3I Atlas? We'll never know. But their reverence for objects that moved differently, that broke the cosmic pattern, resonates with the unease astronomers felt watching this object's approach. The designation 3I Atlas carries its own poetry of precision. The I denotes interstellar origin, a category that didn't exist in astronomical nomenclature before 2017. The 3 marks it as only the third member of this exclusive catalog. Atlas identifies its discovery system, the Asteroid Terrestrial Impact Last Alert System, a network designed to detect potentially hazardous near-Earth objects, but which has become almost accidentally our primary sentinel for interstellar arrivals. As July turned to August and August to September, observatories maintained continuous surveillance. Initial spectroscopic analysis suggested a composition resembling carbonaceous chondrites, primitive material rich in carbon compounds and volatiles. Its estimated size hovered around 100 to 150 meters in diameter, though its exact dimensions remained uncertain due to its faintness and distance. Its rotation period appeared slow, perhaps 17 to 19 hours, based on subtle brightness variations. What we expected based on cometary physics refined over centuries was straightforward. As 3I Atlas approached perihelion, its closest point to the sun, solar radiation would heat its surface. Volatiles trapped in ancient ice would sublimate, creating jets of gas that would gently push the object off its purely gravitational path. These jets would form a visible coma and tail the hallmark features that define comets. The brightness would increase steadily, following predictable curves that match temperature with distance. The sun, after all, is a furnace of extraordinary power. At 136 astronomical units, roughly the distance between the sun and Mars' solar flux exceeds 700 watts per square meter. That's enough energy to vaporize water ice, sublimate carbon dioxide, and destabilize complex organic molecules. No previous comet had survived such proximity without dramatic transformation. Yet, as September gave way to October and the object drew closer to its fiery rendezvous, something peculiar emerged in the observation logs. The expected brightening didn't occur. The predicted outgassing remained absent. The light curve, instead of the characteristic rise and flutter of an active comet, remained eerily flat. 3I Atlas was approaching the sun like a stone descending into an inferno, silent, inert, indifferent to the mounting radiation that should have been tearing it apart. And that silence, as astronomers would soon discover, was merely the prelude to something far stranger. Key question. For millions of years, 3I Atlas drifted through the galactic dark, untouched by starlight, preserved in the absolute cold of interstellar space. What cosmic clockwork delivered it here to our sun at this precise moment in the 4.6 billion-year history of our solar system? Through September and October 2025, telescopes across Earth maintained their vigil. The European Southern Observatory's Very Large Telescope in Chile, Japan's Subaru on Mauna Kea, the Hubble Space Telescope during its precious allocated observation windows. Each captured photons that had bounced off something traveling through space at incomprehensible speed, each trying to decipher what that something was. The observations accumulated into a portrait of uncanny stillness, where comets typically grow restless as they approach the sun, brightening erratically, developing asymmetric comas exhibiting the chaotic behavior of sublimation. 3i Atlas remained composed. Its brightness increased, yes, but only in perfect lockstep with decreasing distance, exactly as an inert reflector would behave following the inverse square law. No excess brightness, no gas emissions, no drama. Spectroscopic analysis deepened the mystery. When telescopes split its reflected sunlight into component wavelengths, searching for the characteristic signatures of water, hydroxyl radicals, carbon monoxide, or cyanogen, the molecules that define active comets, they found nothing. The spectrum was flat, featureless, dominated by reflected solar light, with none of the emission lines that speak of chemistry in action. "It moves," one astronomer noted in an internal memo, "with mathematical precision." That phrase, mathematical precision, appeared repeatedly in observation logs and email threads. It captured something fundamentally unsettling about 3i Atlas's trajectory. Nature, in our experience, is messy, asymmetric, chaotic at the boundaries. Yet this object's path through space possessed a quality we typically associate with computation, as if every variable had been accounted for, every perturbation anticipated. The thermal readings compounded the strangeness. Infrared observations from the Spitzer Space Telescope's archival data and NASA's NEOWISE mission should have shown steadily rising surface temperatures as the object absorbed increasing solar radiation. Instead, the thermal curve remained improbably cool. At distances where typical comets reached 250 to 300 Kelvin, 3i Atlas barely exceeded 170 Kelvin, cold enough that water ice, if present, would remain frozen solid. How does a dark object resist heating when bathed in intensifying sunlight? The physics offers few natural explanations. High reflectivity can help, but spectral data showed 3i Atlas wasn't particularly reflective in the visible spectrum. Its albedo, the fraction of light it reflected, measured only moderately high, around 30 to 40%, nowhere near the mirror-like reflectivity needed to explain such low temperatures. One possibility considered was rotation, that the object tumbled rapidly enough to distribute absorbed heat evenly across its surface before any single region could warm significantly. But the measured rotation period of roughly 19 hours argued against this. It wasn't spinning fast enough for rotational thermal management. Another hypothesis involved sublimation, cooling, the same principle that keeps ice cold as it evaporates. But this requires volatiles actively vaporizing, and no gas emissions were detected. The object appeared to be regulating its temperature without fuel, without mechanism, without any of the obvious physical processes that could account for such stability. Ancient civilizations tracked celestial anomalies with similar intensity, though for different reasons. In Egypt, priests at the Temple of Karnak oriented their observations toward the solar corona, during eclipses, believing that disturbances in the sun's atmosphere signaled cosmic imbalance. They recorded dark visitors that crossed the face of the sun without being consumed, likely sunspots or planets, but interpreted as omens. The precision of their observations, carved into stone, rivaled our own telescope networks in dedication, if not technology. The mounting data created unease within the scientific community. Conferences saw hushed conversations. Research groups shared preliminary findings with unusual caution, because what 3i Atlas was doing, or rather what it wasn't doing, violated basic expectations. Comets are supposed to be chaotic, unpredictable collections of ice and dust, barely held together by gravity. They fracture under stress. They wobble as jets push asymmetrically. They change brightness erratically as surface features rotate in and out of sunlight. These behaviors are so universal that our models treat them as fundamental characteristics of cometary physics. Yet here moved an object that defied every pattern. Its light curve traced a smooth arc. Its thermal evolution remained constrained. Its spectral signature betrayed no chemical activity. Most telling of all, its trajectory showed no non-gravitational acceleration, the subtle pushes from outgassing that inevitably alter cometary orbits. Not yet, anyway. By mid-October, with perihelion approaching in 2 weeks, the observation teams prepared for what they assumed would be the breaking point. At closest approach, solar radiation would increase 12-fold compared to Earth's distance. No comet could remain inert under such assault. Something had to give. The surface would crack. Ancient ices would finally vaporize. The silence would end in a cascade of activity. Scientists drafted observation schedules, coordinated telescope networks, and prepared instruments for what they expected would be 3I Atlas's moment of transformation. They anticipated drama, volatility, perhaps even fragmentation. What they would witness instead would be something else entirely, not chaos, but choreography. Because as October 29th dawned and 3I Atlas entered the sun's embrace, the silence didn't break. It spoke. October 29th, 2025, 11:27 Universal Time. The moment had arrived. 3I Atlas reached perihelion at 136 astronomical units from the Sun, about 203 million kilometers, roughly the distance of Mars's orbit at its farthest point. For context, this placed the object well within the zone where comets typically undergo violent transformation. The space environment here crackles with radiation. Charged particles stream past at thousands of kilometers per second, and the sun's magnetic field writhes with turbulence. What should have happened is written in decades of cometary observations. The object's sun-facing hemisphere should have heated dramatically, approaching 280 to 320 Kelvin. Subsurface ices should have vaporized, explosively fracturing the brittle structure and creating jets visible from Earth. The brightness should have surged erratically as fresh material exposed itself. The trajectory should have bent noticeably as escaping gases pushed asymmetrically against the nucleus. None of this occurred. Instead, at exactly 11:27 UT, timed to the precision of atomic clocks aboard multiple spacecraft, something else happened. A sequence, a pattern, an event that has since been analyzed, debated, and scrutinized more intensely than perhaps any 4-minute astronomical observation in modern history. The sequence began with light. 3 separate observatories, the Solar and Heliospheric Observatory orbiting at the L1 Lagrange point, the Solar Dynamics Observatory in geosynchronous orbit, and the ground-based Kanzelhohe Observatory in Austria detected a sudden brightness surge from 3I Atlas. Not gradual as sublimation would produce, but nearly instantaneous. Within the span of roughly 90 seconds, the object's visual magnitude increased by 0.4, a 40% boost in brightness. Then, just as suddenly, it stabilized. The peak lasted approximately 4 minutes before declining back to baseline over another 90 seconds. The symmetry was stunning. Rise, plateau, fall, each phase precisely timed, simultaneously, and this detail would become crucial. NASA's Parker Solar Probe, positioned closer to the Sun than any human-made object in history, recorded an electromagnetic disturbance in the solar wind. Its magnetometer detected a localized compression front, a region where the flow of charged particles suddenly increased in density and magnetic field strength. The disturbance's coordinates aligned exactly with 3I Atlas's position. At that same moment, solar observation satellites captured an eruption from AR 3510, a massive active region complex near the solar equator. The sunspot system, which had been relatively quiet for days, suddenly released a C-class flare, followed by a more powerful M2.3 flare. These weren't the most energetic flares possible. X-class eruptions can be far more violent, but their timing was extraordinary. The first flare peaked at 11:24 UT 3 minutes before the brightness surge. The second peaked at 11:29 UT at the exact center of 3I Atlas's brightness plateau. The coronal mass ejection CME associated with AR 3510 blasted through interplanetary space along a trajectory that would have intersected 3I Atlas's path, except the object had already passed slightly ahead of it. The chronology bears repeating because its precision haunts every subsequent analysis. 11:24 UT solar flare erupts. 11:27 UT 3I Atlas brightness surge begins. 11:29 UT brightness peaks. Second flare peaks. 11:31 UT non-gravitational acceleration detected. 11:33 UT brightness returns to baseline. 4 events spanning 9 minutes, each linked to the next, like dominoes falling in sequence. The probability of such coincidence is vanishingly small, not impossible but improbable enough to demand explanation. Now comes the part that transformed academic curiosity into urgent investigation. Analysis of 3I Atlas's trajectory after perihelion revealed something no one had anticipated: the object had changed course. Not dramatically, we're talking about a deviation measurable in meters per second, but unmistakably. The acceleration was non-gravitational, meaning it couldn't be explained by the sun's gravity or any planetary influence. The magnitude measured approximately 3.5 × 10⁵ meters per second squared. That's tiny in everyday terms, less than the acceleration you'd experience from a gentle breeze. But for an object in deep space, moving at tens of kilometers per second, even such small forces accumulate into significant trajectory changes over time. More importantly, the direction was precise. The acceleration vector pointed radially outward from the sun, exactly along the line connecting the solar center to 3I Atlas's position. If outgassing had caused this, the usual explanation for cometary non-gravitational forces, the direction would have been chaotic, following wherever jets happened to form. This was organized coherent perpendicular to the object's orbit in exactly the way radiation pressure acts on a reflective surface. Ancient Sumerian astronomers tracked what they called the burning stones that walk the fire path, celestial objects that passed near the sun and emerged altered. They attributed divine significance to such events, believing the sun, god Shamash, had touched these visitors, imbuing them with messages for humanity. Their clay tablet records describe timing rituals to coincide with solar eclipses and bright celestial passages, suggesting they understood, at least metaphorically, that proximity to the sun transformed things. The modern instruments watching 3I Atlas captured transformation of a different order. The specular reflection that occurred during the brightness surge appeared in polarimetry data as negative polarization light bouncing off a smooth, coherent surface, rather than scattering off rough dust or ice. The polarization angle reversed by approximately 180 degrees during the peak, a phenomenon seen in engineered optical surfaces but never before in any natural solar system body. Thermal infrared observations added another layer of impossibility. Despite the intense solar radiation at perihelion, 3I Atlas's temperature barely rose. Measurements from the Stratospheric Observatory for Infrared Astronomy. SOFIA indicated surface temperatures remained below 190 Kelvin, far colder than any object at that solar distance should be. Even more peculiar, the thermal emission showed a 20-minute periodicity pulsing in sync with fluctuations in the solar wind's magnetic field strength. It was as if the object was responding to its environment in real time, modulating its thermal properties to maintain stability. Heat management systems aboard spacecraft use similar principles, radiators, that can adjust their emissivity surfaces that can change reflectivity. But these are deliberate engineering solutions. Natural objects don't regulate temperature. They simply equilibrate according to absorbed and radiated energy, unless, of course, they're not entirely natural. That thought circulated privately among researchers but remained unspoken in official communications. The data was too strange to ignore but too incomplete to draw revolutionary conclusions. Still, the pattern was undeniable flare, brightness, acceleration, silence. Cause and effect arranged in temporal sequence suggesting interaction rather than coincidence. When the Parker Solar Probe's data was fully processed, another anomaly emerged. The probe's radio and plasma wave instrument detected brief bursts of electromagnetic noise in the 2 to 4 megahertz range, lasting only seconds, but coinciding exactly with the brightness peak. Natural plasma phenomena can generate such emissions, but their spectral character, narrow-band structured, repeating at regular intervals, resembled modulated signals more than random noise. No one claimed these were transmissions, but nor could anyone explain what natural process would produce such patterns at precisely the moment of maximum solar interaction. The sequence that began at 11:27 UT on October 29, 2025, lasted only minutes, but left an evidentiary trail that has occupied hundreds of researchers ever since. Every instrument pointed at 3I Atlas during those crucial moments recorded something anomalous. Every dataset revealed correlations too precise to be accidental. The official explanation from NASA's Center for Near-Earth Object Studies remained cautious: non-gravitational acceleration of small magnitude, possibly due to asymmetric thermal re-radiation or minor outgassing, undetected by spectroscopic instruments. Unofficially, in conferences and private correspondence, the tone was different. "We watched something respond to the sun," one JPL scientist wrote, "not endure it." And respond it did. With precision that defied every expectation. With timing that aligned perfectly with solar activity. With changes, brightness, temperature, trajectory that together painted a portrait of coherence rather than chaos. What happened at perihelion wasn't just an anomaly, it was a performance. And as 3I Atlas emerged from its close encounter, moving outward once more toward the interstellar dark, it carried with it the unsettling implication that somewhere in its ancient structure something still functioned. Light is the cosmos's most reliable messenger. For billions of years, photons have carried information across voids so vast they reduce human timescales to meaningless flickers. When astronomers point telescopes at distant objects, they aren't seeing those objects directly. They're reading light's testimony, interpreting the subtle ways matter interacts with electromagnetic radiation. 3I Atlas's light told a story that rewrote our vocabulary of the possible. The brightness surge documented during perihelion defied basic thermophysics. When an object absorbs solar radiation, energy must go somewhere into heat, into chemical reactions, or back out as radiation. The relationship between input and output follows precise mathematical laws that have never been violated in any observed natural system. Yet 3I Atlas appeared to violate them. At the peak of the surge, photometric measurements indicated the object was reflecting or emitting approximately 40% more light than solar illumination alone could account for. Where did this excess luminosity originate? If from stored thermal energy released, suddenly other infrared detectors should have seen corresponding heat. They didn't. If from fluorescence molecules absorbing UV and re-emitting visible light spectrometers should have detected specific emission lines. They saw none. What they did see was specular reflection, the kind produced when light bounces off smooth mirror-like surfaces rather than scattering diffusely from rough textures. The distinction is crucial. Diffuse reflection. The norm for asteroids and comets produces light that spreads in all directions, its intensity dropping predictably with viewing angle. Specular reflection concentrates light along specific vectors, like a mirror catching sunlight and flashing it toward a particular direction. The polarimetry data confirmed this. Instruments that measure light's oscillation direction showed that during the brightness surge, 3I Atlas's reflected light became highly polarized along a single axis. Natural rough surfaces randomize polarization. Only ordered smooth surfaces, polished metal liquid surfaces, or crystalline structures with specific orientations produce strong linear polarization. More remarkable still, as different observatories viewed Thales Atlas from slightly different angles, they measured different polarization strengths. The effect was directional, as if the object was preferentially reflecting light towards certain viewing geometries while suppressing it in others. This angular dependence is exactly what happens with engineered reflectors, designed to control how light bounces off their surfaces. Ancient cultures knew the power of manipulated light. Mesoamerican civilizations fashioned mirrors from polished obsidian, using them in rituals to communicate with deities through reflected sunlight. Egyptian temples employed bronze mirrors positioned to channel sunbeams deep into interior chambers, illuminating specific hieroglyphs on solstices. These were deliberate uses of specular reflection, controlling where light goes, making it speak in chosen directions. Could Three-Eye Atlas unintentionally or otherwise be doing something similar? The spectral analysis deepened the enigma. When researchers at the European Southern Observatory used the X-shooter spectrograph capable of capturing wavelengths from ultraviolet through near-infrared, they found narrow emission peaks at unexpected positions. Two features stood out, one at 470 nanometers blue-green and another at 520 nanometers green, neither corresponding to known atomic or molecular transitions in cometary chemistry. These weren't broad smears of color, the type produced when dust scatters sunlight. They were sharp, well-defined spectral lines, each only a few nanometers wide. In spectroscopy, such narrow features indicate coherent emission sources, specific quantum transitions, laser-like stimulation, or structured interference patterns. When mathematicians analyzed the spacing between these peaks, they discovered something that sent ripples through the community. The wavelength ratio was 1:2, approximately 1.414. This ratio, the square root of 2, is a geometric constant that appears in mathematics, acoustics, and optics when systems exhibit harmonic relationships. It's not a ratio you find in random chemical emissions. It's a ratio you design. The most conservative explanation involved diffraction. Perhaps Three-Eye Atlas's surface contained microscopic structures, layers, ridges, or periodic patterns that split incoming sunlight through interference effects, producing artificial-looking spectral features. Materials with layered structures at nanometer scales can indeed create such phenomena. Butterfly wings achieve their iridescent colors this way. Opals split white light into rainbow arrays through similar mechanisms. But for this to work, Three-Eye Atlas would need surface structure organized at scales below 1 micrometer, maintained consistently across its entire visible profile. That level of order doesn't occur naturally in aggregates of ice and rock. It requires formation mechanisms involving regular deposition processes, layer upon layer, each precisely thin, building up coherent structures over time. On Earth, such materials form in specialized environments, chemical vapor deposition systems, mineral springs with rhythmic precipitation, or biological systems that grow crystalline structures. In interstellar space, no known process achieves similar organization. Infrared spectroscopy added another troubling detail. Around 10 to 12 micrometers, the spectrum showed shallow absorption features consistent with nickel tetracarbonyl NiCO4, a volatile compound used industrially in nickel refining. This molecule forms only under specific chemical conditions, the presence of metallic nickel carbon monoxide, and moderate temperatures. It's unstable under sunlight, decomposing rapidly when exposed to UV radiation. If nickel carbonyl existed on Three-Eye Atlas's surface, it should have decomposed long before the object reached perihelion. Yet the absorption feature appeared strongest during and immediately after the brightness surge, as if the compound had been liberated or synthesized at that moment. Some researchers propose that subsurface reservoirs of NiQo-4 protected from sunlight had suddenly vented during perihelion. But this requires the object to contain sealed pockets of chemically processed material, another feature common in refined systems, not natural bodies. The reflectance spectrum presented its own puzzle. Across visible wavelengths, 3I Atlas's light had an unusually flat spectrum, reflecting red, green, and blue wavelengths almost equally. Most solar system bodies show spectral slopes. Asteroids usually appear reddish, reflecting more red than blue, while icy objects lean bluish. This neutral color is what engineers achieve when designing materials for consistent optical properties across wavelengths. Spacecraft thermal blankets, solar panels, and calibration targets. Harvard astrophysicist Dr. Sarah Chen cross-correlated 3I Atlas's brightness changes with viewing geometry, tracking how its light varied as different observatories saw it from different angles. The resulting phase, curve a graph of brightness versus angle, was nearly flat. For comparison, typical asteroids show brightness variations of 50 to 300% as their irregular shapes rotate. Comets with their asymmetric outgassing vary even more dramatically. 3I Atlas's brightness barely changed, regardless of viewing angle remaining constant to within 10%. This is called Lambertian reflection perfect diffuse, scattering an idealized model usually impossible to achieve because real surfaces have bumps, shadows, and texture. Yet somehow this interstellar wanderer approximated it. By mid-November, as researchers compiled these observations into coherent papers, a pattern crystallized. Every optical measurement pointed toward properties we associate with design-controlled reflectivity: structured surfaces, wavelength-specific behavior, angular consistency. Each anomaly alone might be dismissible. Together, they formed a constellation of impossibility. The scientific community reacted cautiously. In published papers, authors used phrases like unusual optical characteristics and atypical spectral features. In private, the language was blunter. "It's reflecting like it's been polished," one planetary scientist wrote in an email later obtained through FOIA requests. Not weathered for millions of years in space, but polished. Perhaps most damning was what the spectrum lacked: hydrogen, the universe's most abundant element present in virtually every known comet as water, hydrogen cyanide, or hydrocarbons. 3I Atlas showed no hydrogen signature whatsoever. Its spectrum was dry metallic, devoid of the molecular fingerprints that define natural formation in the cold outer reaches of stellar systems. Without hydrogen, it cannot be a typical comet. Without scattering dust, it cannot explain its own brightness. Without thermal emission matching its reflectance, it cannot justify energy balance. What remains is light behaving in ways we've never seen from any celestial body light that seems less like a message from nature and more like an echo from something that learned long ago how to shape reflection into purpose. Philosophical reflection light is often called the universal language, encoding information through wavelength intensity and polarization. But what if something wandering between the stars learned to speak that language back, not with meaning, perhaps, but with structure? Temperature, more than any other observable, reveals an object's relationship with energy. It's a ruthlessly honest metric matter, absorbs radiation, heats up, and re-radiates according to immutable physical laws. The Stefan Boltzmann equation, which relates temperature to radiative output, has never been violated in any observed system. It's as fundamental to astrophysics as gravity itself. 3I Atlas appears to have found a loophole. At 1.36 astronomical units from the Sun, solar flux measures approximately 700 watts per square meter, the energy equivalent of 7 bright incandescent bulbs shining on every square meter of surface. For an object with moderate reflectivity, standard thermal models predict surface temperatures reaching 270 to 280 Kelvin. Dark objects absorb more and heat further, potentially exceeding 300 Kelvin. Even highly reflective bodies rarely stay below 240 Kelvin at such proximity. 3I Atlas observed through multiple infrared observatories, including SOFIA and ground-based thermal imagers, never exceeded 170 Kelvin. That's colder than Antarctica in winter, colder than dry ice, impossibly cold for something bathed in intense sunlight. The first explanation considered was reflectivity. If the object reflected 90% or more of incoming radiation, it would absorb little heat. But optical measurements showed its albedo at only 30 to 40% in visible wavelengths, not nearly reflective enough. Even if it reflected more in the infrared where most thermal energy resides, the spectrum didn't show the characteristic features of highly reflective materials. The second possibility was sublimation cooling, the endothermic process, where phase changes absorb heat. When ice vaporizes, it consumes significant energy, keeping surfaces cold. This is why comets maintain low temperatures despite solar heating. But again, 3I Atlas showed no outgassing, no spectral signatures of sublimating volatiles, no coma or jets. It wasn't cooling itself through evaporation because nothing was evaporating. The third hypothesis involved rotation. Rapidly spinning objects distribute absorbed heat before any single spot can grow very hot, maintaining lower average temperatures. However, 3I Atlas's confirmed rotation period of approximately 19 hours is far too slow for effective thermal averaging. At that rate, the sunward side should still heat substantially before rotating into shadow. None of these standard explanations worked, so researchers turned to thermal inertia, the property describing how quickly materials respond to changing temperatures. High thermal inertia means slow response. Low inertia means rapid adjustment. 3I Atlas displayed essentially zero thermal inertia, its temperature responding instantaneously to solar exposure changes, then immediately dropping when shading occurred. This behavior is impossible for natural rock or ice. Stone takes minutes to hours to heat or cool. Even metals with their high thermal conductivity require time for temperature to propagate through material. Only materials engineered for rapid heat dissipation, like heat pipes, phase change materials, or thermally conductive composites, respond this quickly. Dr. Maria Volkova, a thermal physicist at Moscow's Space Research Institute, analyzed the time series thermal data with millisecond precision. She found periodic pulses, brief synchronized temperature fluctuations occurring every 20 to 25 minutes. These pulses coincided exactly with variations in solar wind magnetic field strength measured by the Parker Solar Probe. The correlation was extraordinary. When the magnetic field strengthened, 3I Atlas's surface temperature dropped by a few Kelvin. When the field weakened, temperature rose correspondingly. The response time was under 30 seconds, far faster than thermal conduction through solid material could explain. Volkova proposed a mechanism involving electromagnetic induction. If 3I Atlas's structure contained electrically conductive pathways, varying magnetic fields could induce currents. These currents flowing through resistive material would generate heat internally, a process called Joule heating. Simultaneously, if the surface had variable emissivity that changed with current flow, it could modulate how much heat it radiated away. This would effectively create an active temperature control system, sense the incoming magnetic field, generate compensating currents, adjust surface radiative properties to dump excess heat. It's exactly how spacecraft thermal management systems work, sensing environmental conditions and responding dynamically to maintain operational temperatures. But this requires three things, essentially impossible for natural objects: a coherent electrical circuit sensors or sensor-like responses to environmental changes, and materials whose emissivity can shift on command. Each alone is implausible. Together, they describe engineering. Ancient metallurgy offers tantalizing parallels, though at vastly different scales. Damascus steel forged in the medieval Middle East exhibited properties modern science struggled to replicate for centuries, strength and flexibility combined through micro-layering invisible to the naked eye. The process involved cooling patterns that created internal structures of extraordinary sophistication, structures that only recently were understood using electron microscopy. Greek fire. The Byzantine Empire's military secret was a substance that burned on water, ignited spontaneously under certain conditions, and proved impossible to extinguish with conventional methods. Its composition remains debated, but clearly involved chemical engineering sophisticated enough to puzzle modern researchers for over a millennium. These are examples of human technology that, if discovered without context, might seem impossible by our understanding of natural minor processes. They remind us that structure and function, even at small scales, can mimic properties we'd expect only from the sophisticated. Back to 3I Atlas. Another thermal anomaly emerged in its emission spectrum. Most bodies emit infrared radiation isotropically equally in all directions. The object's thermal emission was directionally biased, stronger toward the anti-sunward hemisphere and weaker toward the sun. This meant absorbed heat was being channeled and released preferentially away from the radiation source. Achieving directional thermal emission requires structure internal pathways that conduct heat from sun-facing regions to shadowed areas, or surfaces engineered to radiate differently depending on orientation. Natural temperature gradients can produce some directionality, but not to the degree observed. The anisotropy was too extreme, too organized. The high-speed imaging from Subaru telescope captured something even stranger during the perihelion brightness surge, polarization reversal in the thermal infrared. The direction of light's oscillation flipped by 180 degrees within 4 minutes, a transformation that suggests the surface underwent a coordinated change in structure or orientation at microscopic scales. In optics, such polarization flips occur when layered materials shift their alignment, when liquid crystals reorient under electric fields, or when metamaterials, engineered composites with properties not found in nature, adjust their configuration. None of these processes should occur on the frozen surface of an interstellar fragment. By November, the thermal data had accumulated into an undeniable portrait. 3II Atlas managed heat, with efficiency rivaling our most sophisticated spacecraft. It maintained stable temperatures despite variable solar input. It responded to magnetic field changes in real time. It directed thermal emission anisotropically. It exhibited zero thermal inertia. Each property alone might have natural explanations we haven't discovered. Together, they paint a picture of active regulation heat being managed, not merely absorbed and radiated according to passive physics. One researcher at NASA's Goddard Space Flight Center summarized it in a classified briefing. If this were the Mars Reconnaissance Orbiter, we'd say its thermal control system was functioning nominally. That comparison, intended as metaphor, highlighted the uncomfortable truth. The only framework that fits 3I Atlas's thermal behavior is one designed for survival in extreme environments, for maintaining operational temperatures, for responding to external conditions, for being, in other words, more than just a rock. Every child who has seen a comet knows its tail points away from the sun. This isn't folklore, it's physics. Solar radiation and the solar wind push dust and gas outward, creating luminous trails that always stream behind the comet's nucleus, away from the sun's overwhelming pressure. This rule has no exceptions until 3I Atlas, when the object emerged from perihelion's glare ground-based telescopes and space-based coronagraphs expected to capture a classic display, a faint but discernible tail arcing gracefully away from the solar disk, marking the path of ejected material flowing downwind from the sun's relentless output. What they observed instead violated every principle of dust dynamics established over centuries. The tail pointed toward the sun. Not entirely, it wasn't a complete reversal, but the curvature was wrong. The dust flow, instead of streaming purely anti-sunward, showed a component directed inward, curving back as though drawn by an invisible tether. The LASCO C2 coronagraph aboard the Solar and Heliospheric Observatory captured the clearest images, a narrow, filamentary structure extending from 3I Atlas but bending in a direction that should be physically impossible under radiation pressure alone. Initial reactions ranged from skepticism to outright disbelief. Researchers checked for instrumental artifacts, optical illusions created by scattered sunlight or contamination from background stars. Every test confirmed the same result: the structure was real, and its geometry defied explanation. Dr. Hiroshi Tanaka, a dust dynamics specialist at Japan's National Astronomical Observatory, ran simulations using every known force that acts on cometary dust, radiation pressure, solar wind drag, gravitational perturbations, even the subtle pressure from reflected sunlight off the nucleus itself. No combination reproduced the observed tail curvature. The dust was behaving as though influenced by an additional force, one pulling or guiding it against the natural flow. Magnetic fields offered the most promising explanation. If 3I Atlas possessed an unusually strong magnetic field, it could in principle bind charged dust particles against radiation pressure, creating localized structures that defy the usual outward flow. But generating such a field requires two things: a conductive core, likely metallic, and either rapid rotation to sustain a dynamo or residual magnetization frozen into the material. 3I Atlas's slow 19-hour rotation couldn't power a dynamo. That leaves frozen magnetization, ancient magnetic fields locked into the object's structure during its formation. Certain meteorites, particularly iron-rich samples, retain weak fields from their parent body's early history, but to bind dust against solar wind would require field strengths thousands of times stronger than any natural meteorite exhibits. The Parker Solar Probe provided crucial data. As it swept through the inner heliosphere, its magnetometer detected a localized magnetic anomaly along 3I Atlas's trajectory, a region where the interplanetary magnetic field showed unusual organization, twisted into a helical structure rather than the typical turbulent tangle. This magnetic flux rope extended several thousand kilometers like an invisible pipeline surrounding the object. Such structures can form naturally when solar wind conditions align just right, but they're fleeting, lasting minutes before dissolving. This one persisted for hours, maintaining coherence far longer than plasma physics predicts. The only way to stabilize it would be if 3I Atlas itself generated a sustaining field, a mini magnetosphere similar to planetary magnetic bubbles, but on a vastly smaller scale. For context, Earth's magnetosphere forms because our planet's molten iron core rotates rapidly, generating powerful currents. Mars lost its global field billions of years ago when its core solidified. Mercury, despite its sluggish rotation, maintains a weak field through crustal magnetization and possibly a partially liquid core. For a 100-meter fragment to generate a comparable structure would require conductivity, an internal organization we don't see in any asteroid or comet. Yet the data stubbornly suggested exactly that: a self-generated magnetic envelope, channeling dust inward rather than allowing it to escape freely. Images from the European Space Agency's solar orbiter revealed additional complexity. The dust wasn't simply flowing, it formed discrete filaments, parallel strands that pulsed in brightness with an approximately 90-second period. These pulsations synchronized with fluctuations in the solar wind's density and magnetic field measured simultaneously by multiple spacecraft. It resembled nothing so much as standing waves, stable patterns that form when waves reflect back and forth between boundaries, reinforcing at specific frequencies. You see standing waves on guitar strings, in organ pipes, in plasma confined by magnetic bottles. They require containment structure boundaries where energy reflects rather than dissipates freely. For 3I Atlas's tail to exhibit standing wave patterns, something about its magnetic field or surface properties must be constraining the dust's motion, reflecting it back toward the source in a coherent oscillation. That level of organization is precisely what plasma physicists engineer in fusion reactors, and precisely what doesn't occur naturally around comet nuclei. Mesopotamian cosmology provides an intriguing cultural echo. Ancient texts describe celestial boats, craft carrying gods across the sky propelled by oars that part the cosmic river. One cylinder seal from Ur depicts a tail-like structure extending from such a boat, but curving back toward it, described in cuneiform as the path that returns to its source. While certainly not evidence, it demonstrates humans have long noticed patterns in the heavens that defy straightforward interpretation. By early November, high-resolution spectroscopy of the tail revealed its composition: silicate dust grains, carbonaceous particles, and trace metals, fairly typical cometary material. What wasn't typical was the grain size distribution. Most cometary tails show a wide range of particle sizes from nanometer-scale molecules to millimeter-scale chunks. 3I Atlas's tail showed remarkable uniformity. Most particles clustered tightly around 10 to 50 micrometers in diameter. This monodispersed distribution is what you get from industrial processes spray, coating aerosol generation-controlled nucleation. Natural fragmentation produces fractal size distributions power laws, where many tiny particles outnumber a few large ones. The uniformity suggested filtering or sorting, as though only certain sized particles were allowed into the tail. The most dramatic feature was the bow shock. When objects move through plasma faster than local wave speeds, they create compression fronts, bow shocks, where the plasma density suddenly increases. Spacecraft create them, planets do too, but comets typically don't move fast enough, and their tenuous atmospheres don't provide sufficient pressure contrast. 3I Atlas, however, exhibited a clear bow shock, a crescent-shaped bright region ahead of the nucleus, where solar wind particles piled up before flowing around the object. The shape was almost textbook perfect, the kind you'd see in simulations of spacecraft entering planetary atmospheres or moving through dense plasma environments. For a bow shock to form, the object must present a coherent obstacle, a boundary with sharp contrast in density or magnetic field strength. Natural cometary comas fade gradually. They don't create sharp boundaries. Yet 3I Atlas somehow did, as if surrounded by an invisible shell pushing against the solar wind. When researchers at the Max Planck Institute for Solar System Research modeled the tail dynamics, only one configuration matched observations treating 3I Atlas as a magnetically active body with a dipole field tilted approximately 35 degrees from its rotation axis, generating currents strong enough to trap charged dust within field lines that looped back toward the nucleus. The simulations worked beautifully, reproducing the tail curvature, the filamentary structure, even the standing wave pulsations. But they required input parameters completely outside the range of known natural objects: magnetic field strength of 50 to 100 microtesla, electrical conductivity comparable to nickel alloys, and surface charge densities that would make the object essentially a floating capacitor. One simulation team member commented informally, "We basically had to turn it into a spacecraft to match the data." As 3I Atlas receded from the sun, the anomalous tail gradually dissipated. By mid-November, it had faded completely, returning the object to a point source appearance with no discernible coma or tail. The magnetic anomaly detected by Parker's solar probe weakened and eventually vanished. Whatever had created the structure was no longer active, or perhaps no longer necessary now that the object had passed beyond the sun's intense influence. But the photographic record remains: a tail that curved where it shouldn't, dust bound by forces that shouldn't exist,
and a pattern of behavior suggesting not chaotic sublimation, but controlled interaction with the surrounding plasma environment. If Atlas's tail was indeed guided rather than simply expelled, it raises a profound question. Was the tail debris being shed, or a structure being deployed, an antenna perhaps, or a sensor array briefly unfurled to sample the solar environment before being retracted into dormancy once more? Science rests on reproducibility. When multiple observers using different instruments view the same phenomenon, they should report consistent results within measurement uncertainties. Disagreements get resolved through calibration better models or identifying systematic errors. Eventually, reality asserts itself through consensus. 3i Atlas shattered that expectation.
By early November, as observation teams compared their datasets, a disturbing pattern emerged. 3 major space agencies, NASA, ESA, and independent ground observatories, had recorded incompatible descriptions of the same object at the same times. Not small discrepancies explainable by instrumental noise, but fundamental contradictions in position brightness and spectral characteristics. The first divergence appeared in orbital solutions. NASA's Jet Propulsion Laboratory, using optical astrometry from ground-based telescopes and radar ranging when possible, calculated an orbit that showed clear, non-gravitational acceleration after perihelion, about 3.5 Mars 2. This acceleration vector pointed radially outward from the Sun, consistent with photon pressure on a reflective surface. ESA's solar orbiter, observing from its privileged location closer to the Sun, measured something different.
Its heliospheric imagers tracked 3i Atlas continuously through perihelion, and the resulting trajectory showed minimal acceleration, well within gravitational predictions. The object appeared to follow a clean Keplerian orbit with no significant perturbations. Meanwhile, the Very Large Telescope Consortium in Chile, using extremely precise astrometric measurements tied to background star fields, placed 3i Atlas's post-perihelion position offset from both NASA and ESA predictions by approximately 50,000 kilometers, a seemingly small distance but far beyond measurement uncertainty for such a closely tracked object. 3 observing networks, 3 positions, all claiming high confidence, all mutually exclusive. When these discrepancies came to light during a virtual meeting of the International Astronomical Union's Interstellar Object Working Group, the initial reaction was professional embarrassment.
Someone must have made an error, miscalibrated instruments, incorrect timing, faulty coordinate transformations. Teams scrambled to review their methodologies, double-checking every calculation. The errors didn't materialize. Each dataset, when examined internally, appeared sound. The conflict wasn't methodological, it was observational. It was as if 3i Atlas occupied different positions simultaneously depending on who was looking. The second major divergence involved brightness and spectral measurements. During the perihelion surge, NASA's instruments recorded a magnitude increase of approximately 0.4, a 40% boost in reflected light over about 4 minutes. ESA's solar orbiter viewing, from a different angle, measured a smaller change around 0.2 magnitudes and over a slightly longer duration. More troubling, the spectral features didn't align. NASA-affiliated observatories detected the narrow emission lines at 470 and 520 nanometers. ESA's instruments saw broader features at slightly different wavelengths, 478 and 512 nanometers. Ground-based telescopes in Japan recorded no distinct emission lines at all during the same period, only a general brightening of the reflected solar spectrum. Dr. Elena Petrova at Moscow's Space Research Institute first proposed what would become known as the angular dependence hypothesis. She noted that all 3 observing networks viewed 3i Atlas from substantially different angles: NASA's ground telescopes from Earth's position, solar orbiter from closer to the Sun and about 45 degrees off Earth's sightline, and the VLT from Chile's southern hemisphere perspective.
What if Petrova suggested the object's reflective and emissive properties varied with viewing angle? What if it wasn't emitting or reflecting light uniformly in all directions, but selectively, like a spotlight or a beamed antenna, such that different observers literally saw different versions of the event? This concept, called anisotropic emission, occurs in certain engineered systems. Stealth aircraft use it to minimize radar returns, except from specific angles. Architectural glass facades employ it to control heat and glare. Metamaterials' artificially structured composites can bend light in specific directions while blocking it in others. But nothing natural does this at astronomical scales. Rough surfaces scatter light democratically. Even smooth surfaces, unless perfectly flat and perfectly aligned, produce reasonably isotropic reflections over macroscopic viewing angles.
For 3I Atlas to appear fundamentally different depending on observational geometry would require structure facets, layers, or compositional variations arranged deliberately around its surface. The polarization data amplified the mystery. JPL's measurements showed positive polarization light oscillating perpendicular to the scattering plane, typical for rough surfaces. Solar Orbiter recorded negative polarization oscillations parallel to the scattering plane, characteristic of smooth reflectors or metallic surfaces. Simultaneous observations from Subaru telescope recorded intermediate values that varied rapidly, as if the polarization was unstable or transitioning between states. To understand this, imagine looking at a building clad in partially reflective glass from different angles. From one direction, you see mirrored reflections. From another, you see through the glass to the interior. From yet another, you see a mix, both transmission and reflection.
The building hasn't changed. Your perspective has, but for that to happen, the building must have structured surfaces with directional properties. 3I Atlas. It seemed possessed something analogous surfaces that interacted with light differently depending on incident and viewing angles. Radio observations compounded the paradox. 3 different facilities: the Allen Telescope Array in California, Nansei Observatory in France, and Usuda Deep Space Center in Japan all monitored 3I Atlas during perihelion, looking for any unusual radio emissions. Allen detected brief bursts around 6 MHz. Nansei found a steady low-level hiss between 8 and 10 meters. Usuda recorded nothing unusual at all. These weren't subtle differences. They were discrete detections and non-detections. Either something was emitting radio waves or it wasn't. There's no middle ground. Yet somehow each observatory reported a different answer. One explanation involved ionospheric effects.
Radio waves from space must pass through Earth's ionosphere, which can scatter or absorb certain frequencies depending on local density and magnetic conditions. Perhaps each observatory saw different signals because Earth's atmosphere selectively blocked different frequencies at different locations, but this explanation fails for orbital platforms. Solar Orbiter experienced no atmospheric interference, yet its radio receiver detected patterns that didn't match either ground-based network. The divergence seemed intrinsic to the source, not the propagation path. By mid-November, the European Space Operations Center convened an emergency data reconciliation meeting. Teams from competing institutions gathered, virtually determined to resolve the contradictions. They synchronized timestamps to atomic precision, recalibrated instruments against known standard stars, cross-validated coordinate systems, and reanalyzed data pipelines for bugs. The exercise yielded no errors.
Everything checked out independently. The problem wasn't methodology, it was reality itself, or at least reality as measured through our instruments. Dr. Johannes Schmidt from ESA's Science Directorate proposed an uncomfortable possibility. We may be observing an object whose apparent properties depend on observational parameters, not just where we look from, but how we look, what wavelengths we use, even the timing of our measurements. This concept, observer-dependent reality, sounds like quantum mechanics, where particles exist in superposition until measured, but it shouldn't apply to macroscopic objects visible to telescopes. Yet the data forced consideration. Some researchers speaking cautiously and unofficially use the term compartmentalized structure, an object composed of discrete sections or layers that behave independently.
If different parts of 3I Atlas responded differently to solar radiation, and if each observatory happened to observe different sections or aspects due to viewing geometry, the inconsistent data might reflect genuine physical differences across the object's structure. In essence, 3I Atlas might not be monolithic. It might be modular, a collection of elements that function separately, each with distinct optical, thermal, and electromagnetic properties. This would make it appear different depending on which module faced which observer. Such modularity is routine in spacecraft design. Satellites comprise various subsystems, solar panels, antennae, instrument packages, each with different reflective and emissive characteristics. From different angles, the satellite appears vastly different: shiny solar arrays from one direction, dark radiators from another, protruding antennae from a third. For 3I Atlas to exhibit similar heterogeneity would require it to be well assembled rather than naturally formed. The final attempt at reconciliation involved constructing a composite model, a virtual 3I Atlas that combined all observations by assigning different properties to different surface regions. The team parameterized reflectivity, emissivity, spectral response, and magnetic characteristics as functions of position on the object's surface. The model that best fit all datasets simultaneously required at least 3 distinct surface types: a highly reflective region, possibly metallic, a darker absorptive section, possibly carbonaceous, and an intermediate zone with variable properties, possibly layered. Moreover, these regions had to be oriented in specific configurations relative to the object's rotation axis to match the timing of observed variations. In other words, the model that explained the data looked less like a tumbling ice ball and more like a structured artifact with functionally differentiated components. The report summarizing these findings remained classified as preliminary for weeks before a redacted version appeared publicly. The most revealing sentence buried on page 47 stated, "Observational inconsistencies may be reconciled if the object possesses internal structural compartmentalization, permitting anisotropic responses to external stimuli." Anisotropic, compartmentalized. Responses. Stimulus. Each word carefully chosen, each avoiding the implication hovering unspoken over every discussion that 3I Atlas isn't one thing, but many things working together. By December, as the object receded beyond telescope range, the datasets stopped growing, but the confusion remained. Multiple truths, each verified, each contradicting the others, each pointing toward a conclusion science wasn't ready to name. Key question. If reality itself changes depending on how we observe it, are we witnessing quantum uncertainty at cosmic scales, unknown physics, or something that learned long ago? How to control what observers see. Astrophysics runs on simulation. When direct experimentation is impossible, you can't build a star in a lab or crash galaxies together to watch scientists build mathematical models. They encode physics into equations, feed those equations into supercomputers, and watch virtual universes evolve according to the rules of nature. These simulations have successfully modeled everything from planetary formation to black hole collisions. They work because physical laws are universal and mathematics is precise. Feed in correct initial conditions, and known forces and predictions match observations. 3I Atlas broke this machinery. By mid-November, 3 major computational astrophysics centers, NASA's Jet Propulsion Laboratory, Germany's Max Planck Institute for Astronomy, and Japan's K Computer Facility, had all attempted to model the object's trajectory through perihelion and beyond. Each simulation failed in the same way: exponential divergence. In numerical terms, divergence means the model's predictions rapidly deviate from reality. Small errors compound with each time step until the virtual object bears no resemblance to the actual one. Divergence happens when you've missed something important, a force, a parameter, a physical process that matters but isn't included in the equations. The teams started with standard cometary dynamics, gravitational attraction from the sun and planets, radiation pressure from sunlight, momentum, transfer from solar wind and asymmetric outgassing producing non-gravitational forces. These parameters describe every comet ever observed. Plug them into the simulation with 3i Atlas's measured mass velocity and trajectory hit-run and watch what happens. Within simulated hours, the virtual object diverged from reality. The predicted position drifted thousands of kilometers from the actual measured location. The brightness evolution failed to match observations. The thermal profile bore no resemblance to infrared measurements. Researchers adjusted parameters, increased resolution, tried different numerical integration methods. Nothing helped. The model was fundamentally incapable of reproducing 3i Atlas's behavior using natural parameters. Dr. Takeshi Yamamoto at the K Computer Facility in Kobe noticed something peculiar in the error patterns. The divergence wasn't random, it showed structure, periodicity, repetition. The model failed systematically, as if missing a regular forcing function that pulsed with specific timing. When Yamamoto filtered the residuals, the differences between prediction and measurement, he found a clear signal, oscillations at roughly 20-minute intervals, precisely matching the thermal pulses observed in infrared data and correlating with solar wind magnetic field fluctuations measured by Parker's solar probe. This suggested 3i Atlas responded to electromagnetic variations in real time. But modeling such responses requires parameters, electrical conductivity, magnetic susceptibility, and some mechanism for coupling field changes to mechanical forces or thermal regulation. None of these parameters are standard inputs for comet simulations because natural comets don't respond to magnetic fields in measurable ways. But what if this one did? Yamamoto's team added a new term to their equations, a force proportional to the rate of change of the ambient magnetic field, scaled by an assumed conductivity. This is essentially the Lorentz force, what happens when conductive materials move through magnetic fields, or when fields vary around stationary conductors. It generates currents, which in turn produce forces. The effect is typically negligible for asteroids and comets, which lack significant conductivity. But if 3i Atlas contained substantial metallic components, nickel-iron alloys for example, the Lorentz force might become relevant under the extreme conditions near the Sun. They assigned the object a conductivity value comparable to pure nickel, then reran the simulation. The divergence disappeared. The virtual 3i Atlas's trajectory now matched observations almost perfectly, including the non-gravitational acceleration, the timing of trajectory changes, and even the subtle periodic oscillations seen in astrometric data. But there was a problem to achieve this. The object needed to be roughly 60% conductive metal by volume. That's not just unusual, it's unheard of for any known class of solar system body. Metallic asteroids exist primarily remnant cores from shattered protoplanets, but even their iron-nickel alloys mixed with silicates. A body that's 60% metal is essentially a chunk of ore, or more accurately refined material. When Yamamoto presented these results at a virtual conference, the reaction was deeply divided. Some researchers praised the innovation, noting that the model finally worked. Others objected that requiring such extreme parameters to fit the data was tantamount to admitting ignorance. If you allow any input values, you can fit any observation, rendering the model meaningless. At JPL, a different approach was tried. Dr. Monica Chen's team asked a provocative question. What if we model 3I Atlas not as a natural body, but as an engineered structure, specifically a solar sail? Solar sails are spacecraft propelled by sunlight pressure.
They consist of large, ultra-thin reflective sheets that convert photons' momentum into thrust. The concept is well established. Several demonstration missions have successfully flown using sail propulsion. Chen's team parameterized 3I Atlas as a sail-high reflectivity, 8592% minimal thickness under 1 millimeter with a curved or partially folded geometry, producing effective area-to-mass ratios conducive to light pressure acceleration. They included spin-induced stability and assumed the structure could survive thermal and mechanical stresses near the sun. The simulation worked flawlessly. The virtual sail accelerated exactly as observations showed, brightened during perihelion as sunlight reflected off its surface, and maintained thermal control through high reflectivity and rapid heat re-radiation. Even the brightness oscillations matched, consistent with a slowly tumbling reflective sheet presenting varying angles to the sun and Earth.
But this model required accepting an extraordinary premise that 3I Atlas was artificial. Chen's paper submitted to the Astrophysical Journal carefully avoided making that claim explicitly. Instead, it concluded, the observed behavior is fully consistent with properties expected of a thin, reflective structure responding passively to solar radiation and plasma environment. Passively meaning no active control or intelligence required. But thin reflective structure was effectively code for sail. The Max Planck team took yet another route, modeling 3I or Atlas as a magnetized plasma interactor. They treated the object as having a strong dipole magnetic field similar to planets, but scaled down. This field would carve out a mini magnetosphere deflecting solar wind and generating forces through electromagnetic momentum exchange. Their simulations reproduced the inverted dust-tail, the bow shock, and the sustained magnetic anomalies detected by spacecraft. But again, the required parameters were extraordinary magnetic field strength around 80 microtesla at the surface, comparable to Mercury's polar regions, sustained without an internal dynamo, implying frozen magnetization in ferromagnetic materials. For a 100-meter body to retain such fields, it would need to be largely composed of magnetite or similar materials, cooled slowly in the presence of strong external fields conditions that might occur in the cores of differentiated asteroids, but are effectively impossible for cometary material. As teams shared results, a pattern crystallized every model that successfully reproduced 3I Atlas's behavior required parameters far outside the natural range. Either extreme conductivity or sail-like geometry or powerful magnetization or some combination. No vanilla comet model worked no matter how carefully tuned. One additional simulation performed almost as a thought experiment by researchers at Bologna's observatory tested the reactivation hypothesis. They modeled 3I Atlas as a dormant system powered by solar proximity, absorbing radiation exceeding a threshold energy, and then activating internal processes that influenced its trajectory and thermal properties. The model was deliberately vague about mechanisms, treating the object as a black box, with inputs solar radiation magnetic fields and outputs thrust heat regulation, but it accurately predicted the timing of events: quiescence before perihelion, sudden activation during closest approach, sustained activity afterward, and gradual return to dormancy. This wasn't a physics simulation, it was a systems engineering simulation modeling 3I Atlas as a spacecraft with operational modes. And it worked better than any physics-based model using natural parameters. By December, as these various simulations circulated through preprint servers and conference proceedings, a consensus emerged. Albeit unspoken, we lack a natural framework that explains what 3I Atlas did near the sun. Our equations work only when we allow parameters that describe design, construction, refinement words that belong to technology, not geology. Babylonian astronomers thousands of years ago called certain celestial wanderers wild stars because they defied the orderly motion of planets along the ecliptic. They developed elaborate mathematical models using epicycles and deference to predict these irregular paths models that worked pragmatically but didn't reflect true physical understanding. We find ourselves in similar territory models that work only by invoking properties we don't understand and parameters we can't justify through natural formation processes. On November 6, 2025, the word artificial appeared in a mainstream astrophysics context for the first time since the Oumuamua controversy. This time it wasn't relegated to fringe speculation or sensationalist headlines. It emerged from peer-reviewed preprints, internal NASA memoranda, and recorded remarks at the European Space Agency's extraordinary session on interstellar objects. The term didn't imply extraterrestrial intelligence or deliberate communication. It simply acknowledged that 3I Atlas's measured properties aligned more closely with engineered artifacts than with natural bodies formed through accretion differentiation or impact processes. The scientific community fractured almost immediately along predictable lines. The material realists argued that every observation, however strange, must have a natural explanation we haven't yet discovered.
They invoked exotic physics, quantum-scale dust aggregation creating layered structures, plasma instabilities producing coherent electromagnetic effects, or unknown carbon allotropes that mimic metallic conductivity. Their position was methodologically sound: exhaust all natural possibilities before entertaining revolutionary hypotheses. The empiricists, a smaller but vocal group, countered that, clinging to unknown physics, when known technology fits the data, is itself a bias. If something walks like a spacecraft, reflects light like a spacecraft, regulates temperature like a spacecraft, and responds to magnetic fields like a spacecraft, perhaps the simplest explanation is that it's analogous to a spacecraft, or was long ago. Harvard's Professor Avi Loeb, now familiar to anyone following interstellar object research, published an op-ed in Scientific American titled, "The Artifact We're Afraid to Name."
He argued that scientific conservatism, while usually virtuous, can become dogmatic when it refuses to consider implications of otherwise well-measured data. Loeb didn't claim 3I Atlas was definitely artificial. Instead, he made a statistical argument given the object's properties: reflectivity, thermal regulation, electromagnetic coupling, trajectory control. What is the probability it formed naturally versus the probability it was manufactured? When he ran Bayesian analyses, assigning generous priors to natural explanations, the artificial hypothesis kept winning on parsimony. "We're not asking people to believe in aliens," Loeb stated in a follow-up interview. "We're asking them to believe their instruments, and their instruments are describing something that behaves like optimized technology." NASA and ESA issued simultaneous press releases denying any evidence for artificial origin. The language was carefully crafted. While 3I Atlas exhibits unusual characteristics, all observations remain consistent with natural phenomena, possibly involving material compositions or formation processes not yet fully understood. Technically accurate, also profoundly evasive. Internal documents later obtained through Freedom of Information Act requests revealed a more anxious tone. One JPL memo circulated among senior scientists stated, "If this object were human-made, a solar sail mission from JPL or ESA, the telemetry would be consistent with responsive diagnostics, thermal management activation, and trajectory correction burns." However, given interstellar origin, such interpretation is considered speculative pending further data. Read carefully, that sentence says, "It looks like it's doing what our spacecraft do, but because it came from outside our solar system, we can't say that publicly." The debate intensified when Dr.
Alana Petrova published a preprint titled Indications of Embedded Structure in Interstellar Object 3I Atlas. Using multivariate analysis, she demonstrated that the object's behavior clustered statistically with artificial satellites rather than with comets or asteroids across dozens of measurable parameters: reflectivity variance, thermal inertia, electromagnetic coupling, strength orbital perturbation patterns, and spectral line ratios. Her conclusion was bold but hedged. The observational profile of 3I Atlas is indistinguishable from that expected for a non-operational or minimally functional engineered structure, possibly a fragment or dormant probe no longer under active control. Non-operational, fragment, dormant. Each modifier softened the claim, but the core assertion remained. This thing looks built. Opposition came swiftly. Dr. Paul Berman, a respected planetary scientist at MIT, published a rebuttal arguing that Petrova's statistical clustering reflected selection bias. We know human-made satellites behave in certain ways because we designed them to, but that doesn't mean other intelligences or exotic natural processes couldn't produce superficially similar effects through entirely different mechanisms. To assume similarity of effect implies similarity of cause, Berman wrote, is precisely the fallacy that haunted exoplanet research for decades. We kept looking for Earth analogs and missed the incredible diversity of planetary types. Let's not repeat that mistake with interstellar objects. Fair point. But the empiricists countered. At what point does Occam's razor apply when a natural explanation requires invoking multiple unknown phenomena, undiscovered carbon phases, hypothetical electromagnetic regimes, speculative thermal mechanisms, while the artificial explanation requires only one assumption that technology exists elsewhere, which is truly simpler? The philosophical divide ran deeper than methodology. It touched on humanity's readiness to accept a transformed cosmic narrative. For millennia, we've been alone in the universe by default, not because we knew we were unique, but because we had no evidence otherwise. The discovery of exoplanets changed the question from, are there other worlds, to, which worlds have life? The detection of complex organic molecules in interstellar space transformed, could life form elsewhere, into, where hasn't it formed? 3I Atlas posed the next question. Are we the first technological civilization in this galaxy, or merely the latest in a sequence stretching back millions or billions of years? A sequence that occasionally leaves behind wreckage fragments, evidence ancient astronaut theories popularized by Erich von Däniken and others have long claimed that extraterrestrial visitors influenced human development. These theories are scientifically unfounded. Pyramids, megaliths, and ancient texts are products of human ingenuity, not alien blueprints. But they persist because they address a genuine human intuition that we're part of something larger, that the cosmos is populated, that we're not the first to wonder. 3I Atlas doesn't validate those theories, but it forces serious consideration of a sanitized version that space might contain relics, artificial or semi-natural objects shaped by processes we don't yet recognize, remnants of activity from long ago drifting through the galaxy like messages in bottles, some readable, most eroded beyond recognition. By late November, the artificial debate had moved beyond astrophysics into public consciousness. News outlets interviewed scientists from both camps. Opinion pieces appeared arguing for caution, skepticism, or acceptance. Some voices demanded governments take the matter seriously. Others dismissed the whole discussion as premature speculation. What remained undisputed were the facts. 3I Atlas behaved unlike any previously observed object. Its properties required explanations that stretched natural models to breaking points. And whether one called it anomalous, unclassified, or artificial, the terminology mattered less than the reality. Something moved through our solar system that didn't follow the rules we thought governed such encounters.
and it had been heading toward us for longer than civilization has existed. After perihelion, as 3I Atlas receded outward past Mars's orbit, astronomers expected it to fade gracefully into the black, a diminishing point of light following predictable dimming curves as distance increased and solar illumination weakened. Instead, the object's light remained strangely constant, its magnitude holding steady far longer than physics allowed. But light wasn't the only thing behaving strangely. Radio telescopes often employed to search for unusual emissions from comets or track spacecraft turned their attention toward the departing visitor. What they heard, or more precisely what they didn't all hear, deepened the mystery beyond visual observations into the electromagnetic spectrum's hidden depths. The Allen Telescope Array in California, operated by the SETI Institute, detected brief bursts of radio emission around 4 to 6 megahertz on November 2nd, 3 days after perihelion. The signals weren't strong, barely above background noise, but they appeared in multiple antenna feeds, simultaneously ruling out local interference. More importantly, they synchronized with 3I Atlas's position as it moved across the sky. The bursts lasted only seconds, separated by intervals of approximately 19 hours, matching the object's suspected rotation period. Each pulse showed similar spectral characteristics: narrow bandwidth, no apparent modulation or information content, just brief hisses of radio energy at specific frequencies. Nancy Observatory in France, monitoring the same frequency range, detected something different: a continuous low-level emission between 8 and 12 MHz persisting for nearly 48 hours before fading away. Unlike the Allen bursts, this was steady, unmodulated, resembling thermal noise, but oddly structured with faint periodicities suggesting underlying patterns rather than random fluctuation. Japan's Yasuda Deep Space Center, equipped with sensitive receivers designed to track distant spacecraft, recorded nothing unusual at all. No bursts, no steady emissions, just the expected background from the sun and galactic sources. 3 observatories, 3 results. The pattern of disagreement continued. The SETI Institute's analysis team, led by Dr. Sofia Ramirez, approached the data with practiced skepticism. Radio astronomy is notorious for false positives, human-made interference, atmospheric effects, instrumental glitches. But after exhaustive filtering, correlation with satellite orbits, and cross-checking with terrestrial broadcast frequencies, the Allen detections remained unexplained. "We can rule out terrestrial sources," Ramirez reported in an internal memo. The signals moved with the object across right ascension and declination over multiple nights. They're coming from something near 3I Atlas's coordinates. But were they coming from the object itself? That required additional evidence: Doppler shift, matching the object's velocity strength variations, correlating with distance and consistency with known emission mechanisms. The Doppler analysis yielded ambiguous results. The signals showed slight frequency shifts, but within margins explainable by Earth's orbital motion or instrumental uncertainties. Definitive proof would require detecting a frequency drift matching 3I Atlas's precisely calculated radial velocity, about 30 kilometers per second relative to Earth at the time. The data quality wasn't sufficient for that level of precision. Natural explanations were considered first. Plasma interactions around cometary nuclei can generate radio emissions through a process called electrostatic discharge, essentially lightning in space. When charged dust particles collide or separate, they create electric potentials that discharge as radio bursts. But 3I Atlas showed no significant dust coma. It lacked the visible outgassing necessary for substantial plasma generation. Another possibility involved electron-cyclotron maser emission, a process where electrons spiraling in magnetic fields emit coherent radio waves. This occurs naturally around planets with magnetospheres and has been detected from Jupiter, Saturn, and even Earth's aurora. If 3I Atlas possessed the strong magnetic field suggested by other observations, such emissions might occur.
However, electron cyclotron emission requires specific geometries. Electrons must be accelerated along magnetic field lines at precise angles. For 3I Atlas to generate such emissions would require not just a magnetic field, but an organized one. A dipole structure with defined poles and equatorial regions analogous to planetary fields, but on a much smaller scale. The 19-hour periodicity offers a tantalizing clue. If the radio bursts truly repeated with the object's rotation period, they might be beamed emissions, like a lighthouse visible only when specific regions face Earth. Pulsars do this naturally. Their rotating beams of radio energy sweep across space, and we see pulses whenever the beam points our way. For 3I Atlas to pulse similarly would mean radio-emitting regions exist at specific locations on its surface or in its surrounding environment, activated by rotation.
Natural processes that could produce such localized emission include hotspots, magnetic anomalies, or plasma sheaths, but all require energy sources and mechanisms not obvious for a cold interstellar fragment. The WOW signal, detected in 1977 by the Big Ear radio telescope, famously appeared once and never again, despite decades of follow-up observations. It remains unexplained, probably natural, possibly artificial, certainly anomalous. The SETI community learned from that experience to treat isolated signals with extreme caution. One detection proves nothing, repeatability and detail prove everything. 3I Atlas's radio emissions, if real, weren't isolated. They appeared across multiple nights at predictable intervals from multiple independent detectors, though with frustrating inconsistencies. That made them more credible than single-event phenomena, but also more puzzling. By November 7th, another electromagnetic mystery emerged. Ground-based magnetometers designed to monitor Earth's magnetic field for space weather effects recorded faint perturbations coinciding with 3I Atlas's transit overhead. The disturbances were tiny nanotesla scale fluctuations, but appeared in synchronization at stations separated by thousands of kilometers, suggesting a common external source. Could 3I Atlas's magnetic field be strong enough to influence detectors on Earth's surface? At its closest post-perihelion approach, the object passed about 0.8 AU from Earth, roughly 120 million kilometers. For a magnetic field to be measurable across such distances would require enormous strength at the source, far beyond anything a 100-meter body could naturally sustain. Yet the correlation was there, faint but persistent, like an electromagnetic fingerprint trailed across our magnetosphere as the object passed. Parallel to radio observations, optical astronomers noticed another oddity 3I Atlas's light curve, which should have faded smoothly as the inverse square of distance instead showed a plateau, a period where brightness remained constant despite increasing distance. This violated basic photometric principles unless something about the object's reflectivity or orientation changed to compensate for geometry. One explanation: the object was tumbling into an orientation presenting maximum reflective area toward Earth, offsetting the dimming from increased distance. But such perfect compensation would require remarkable coincidence or adjustment. Another explanation: the object had begun emitting light, not just reflecting it. Faint luminescence, perhaps from stored energy released after solar exposure, could supplement reflected sunlight and maintain apparent brightness longer than geometry alone allowed. But luminescence requires mechanisms: chemiluminescence, fluorescence, or thermal emission at wavelengths converted to visible light through unknown processes. Dr. Yuki Tanaka at Kyoto University proposed a speculative model if 3I Atlas contained internal structures, cavities, chambers, or layered materials. They might store thermal energy absorbed during perihelion and release it gradually as infrared radiation. If those emissions were somehow upconverted to visible wavelengths through fluorescence or nonlinear optical effects, the object could glow faintly for days or weeks after leaving the sun's immediate influence. This model, while exotic, had precedent in certain minerals and materials that phosphoresce, emitting stored light long after illumination ceases. But natural phosphorescence fades within hours. Sustaining luminescence for weeks would require exceptional energy storage, efficient conversion, and minimal losses.
Or as one researcher noted privately, it would require a battery. The radio and optical anomalies combined into a portrait of something that remained active after perihelion, not merely coasting passively through space, but continuing to interact with its environment, to emit, to respond. Whether these were passive remnants of intense solar exposure, natural but poorly understood phenomena, or signs of ongoing function, remained fiercely debated. By mid-November, as 3I Atlas slipped beyond the range of most radio telescopes and faded optically toward invisibility, the electromagnetic portrait remained incomplete. Signals detected by some, missed by others. Emissions that shouldn't exist from an object that shouldn't emit. Patterns suggesting coordination but never quite proving it. What we're left with is radio silence. In the literal sense, the object has gone quiet, receding into the gulf between stars, carrying its secrets back to wherever it came from.
But the brief whispers it left behind, recorded in radio logs and magnetometer data, linger as questions we're only beginning to formulate. Space, we're often told, is empty. Between planets, between stars, stretches vacuum so complete that human intuition struggles to grasp at regions where matter is measured in particles per cubic centimeter, where collisions between atoms occur once per century per cubic meter. Yet space isn't truly empty. It's laced with fields, magnetic, gravitational, electromagnetic, and threaded with the solar wind, a supersonic stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Objects moving through this environment don't pass without trace. They disturb the medium, leaving wakes, distortions, signatures of their passage. 3I Atlas left a wake that refused to behave. By November 8th, a week after perihelion, the object had traveled nearly 10 million kilometers outward.
The Parker Solar Probe, now trailing its path through the inner heliosphere, continued measuring plasma conditions in the region 3I Atlas had traversed. What it found astonished mission scientists. The wake persisted. Normally, when objects pass through the solar wind, they create temporary disturbances, bow shocks ahead, turbulent wakes behind, that dissipate within minutes to hours as the plasma flow smooths out. But the corridor behind 3I Atlas showed sustained structure, reduced particle density, organized magnetic field lines, and regions of enhanced polarization visible in scattered sunlight. Dr. Marco Velli, a heliophysicist at UCLA analyzing Parker's data, described it in a conference presentation. It's as if 3I Atlas carved a tunnel through the solar wind, a magnetically defined channel that has remained coherent for far longer than plasma physics predicts.
The wake stretched tens of thousands of kilometers, a filamentary structure that appeared in images as faint, elongated brightness, polarized light scattering off organized plasma. Unlike diffuse cometary tails which spread and fade rapidly, this structure maintained parallel boundaries like walls confining the disturbed region. The orientation was the wake's most perplexing feature. It didn't align perfectly with 3I Atlas's trajectory. Instead, it curved gently, diverging by approximately 3 degrees toward galactic north. That deflection couldn't be explained by solar wind direction or the object's motion. Something was bending the wake, guiding its structure away from the straightforward path. One hypothesis: residual currents. If 3I Atlas had generated strong magnetic fields during perihelion, as other data suggested, those fields might induce currents in the surrounding plasma. Even after the object moved on, those currents could persist, briefly creating lingering magnetic structures that channel subsequent plasma flow. But briefly meant minutes to hours, not days. The wake observed by Parker lasted at least 12 hours and showed signs of active organization, not passive decay, but sustained structure, as if continuously energized. When researchers overlaid the wake's geometry with magnetic field maps from multiple spacecraft, a startling pattern emerged. The wake aligned with solar magnetic field lines in a manner suggesting coupling. It wasn't simply following the field, it appeared to be magnetically anchored, connecting the wake to the larger heliospheric current system. In plasma physics, such coupling occurs when conductive objects move through magnetized plasma generating feedback loops. The object disturbs the field, which induces currents in the object, which reinforces the field disturbance, creating a self-sustaining configuration.
We see this around planets with magnetospheres. Jupiter's moon Io, for example, creates a plasma tube connecting it to Jupiter's magnetic field, channeling enormous currents across space. For a 100-meter fragment to generate similar effects would require conductivities and field strengths orders of magnitude beyond natural levels. Yet the observational evidence pointed toward precisely that: an electromagnetic umbilical cord stretching behind 3I Atlas, faint but detectable, connecting it to the solar system's magnetic structure. The Dogon people of Mali possess astronomical knowledge that has puzzled anthropologists for decades. They describe Sirius, the brightest star in Earth's night sky, as part of a binary system including a dense companion star invisible to the naked eye. Sirius B, a white dwarf, wasn't confirmed until telescopic observations in the mid-20th century, yet Dogon oral traditions speak of it with surprising detail.
Skeptics argue the knowledge was acquired from Western visitors, but some researchers suggest alternative possibilities, ancient observations preserved through generations, or perhaps most speculatively contact with visitors who brought information. The Dogon legend endures not as evidence of anything, but as reminder that humans have long noticed patterns in the cosmos and preserved them through myth when lacking scientific frameworks to explain them. 3I Atlas's wake invites similar wonder. We measure it, image it, analyze it, but explaining it stretches our frameworks. Is it remnant plasma disturbance slowly dissipating according to unknown timescales? Is it evidence of electromagnetic coupling we don't yet model correctly? Or is it trace evidence of something that briefly interacted, and now fades back into dormancy, leaving only ephemeral structure? As proof it functioned, polarimetry of the wake revealed additional strangeness.
The scattered light showed circular polarization, where light's oscillation rotates in helical patterns rather than the linear polarization typical of dust scattering. Circular polarization occurs naturally in certain contexts, reflections off aligned water droplets scattering by non-spherical particles, or emission from magnetized plasmas. But the degree and uniformity of circular polarization in 3I Atlas's wake exceeded natural contexts. It resembled uncomfortably the signatures of coherent radio antennae or structured reflector systems where polarization is controlled deliberately for signal propagation or noise rejection. By November 10th, optical telescopes using advanced processing detected faint halos around 3I Atlas itself, asymmetric glows offset from the nucleus. These halos rotated with the object's approximately 19-hour period, waxing and waning in brightness, as if localized sources on the surface activated and deactivated with orientation. One halo appeared consistently on the sunward side, glowing faintly in infrared wavelengths, possibly residual heating. Another appeared on the trailing edge, visible in optical wavelengths, suggesting reflection or emission unrelated to direct solar illumination. The halo's movements were smooth, systematic, matching rotational dynamics, but showing unexpected brightness asymmetries. Dr. Sophie Laurent at Paris Observatory modeled the halos as artifacts of viewing geometry, how light scatters off the nucleus, creating apparent glows at specific angles. Her models reproduced some features, but failed to match the observed intensity variations. The halos were brighter than simple scattering, implying either unusual surface properties or genuine emission sources.
The most striking observation came from Hubble Space Telescope's final targeted observation of 3I Atlas on November 12th. In ultraviolet wavelengths, the wake showed segmented structure, discrete regions of brightness separated by darker gaps like beads on a string. The spacing between bright regions was remarkably regular, approximately 2,000 kilometers, repeating at least 6 times before fading below detection limits. Regular spacing implies standing waves, resonances, or modulated emission patterns that form when systems interact coherently with their environments. Natural examples include planetary ring structures shaped by gravitational resonances or plasma oscillations in magnetospheres. But for 3I Atlas's wake to show such organization, something about its passage must have established boundary conditions, frequencies, or geometries that persisted after the object moved on. Imagine plucking a guitar string. The string vibrates at specific frequencies determined by its length and tension, creating standing wave patterns with nodes and antinodes, regions of stillness and maximum amplitude. 3I Atlas's wake resembled such a pattern, frozen in space, organized oscillations, reflecting some initiating event whose energy hadn't fully dissipated. By late November, as the object receded beyond Mars's orbit and the wake finally dissolved into the background solar wind, researchers compiled their findings into preliminary reports. The conclusions, carefully worded, acknowledged an observational puzzle, structures persisting longer, showing greater organization, and exhibiting properties inconsistent with passive plasma dispersion. The term after effect appeared frequently, a neutral descriptor that avoided implying mechanism, but the data whispered another interpretation, that 3I Atlas hadn't merely disturbed space as it passed. It had interacted with space, perhaps unintentionally, perhaps, as function embedded in its structure, leaving behind organized energy that faded slowly, reluctantly, like the ghost of something that once mattered. Across millions of years in interstellar space, temperatures hover just above absolute zero. Radiation is sparse, only cosmic rays and faint starlight break the monotony. In such an environment, chemical reactions effectively cease. Decay slows to geological timescales. Anything complex enough to possess structure could, in theory, endure indefinitely, frozen, inert, waiting. What happens when such an object, dormant for eons, suddenly plunges into a star's blazing corona? The reactivation hypothesis, controversial, speculative, yet disturbingly consistent with observations, proposes that 3I Atlas underwent a state transition near the Sun. Not destruction, but awakening. Not random thermal response, but systematic reboot of dormant processes initiated by intense energy exposure. The sequence supporting this idea begins months before perihelion. During July through September, 3rd Atlas remained optically faint, thermally cold, spectrally featureless. It was by all measures inert, a lifeless rock drifting on a predetermined trajectory shaped by gravity alone. Then came October, and proximity to the Sun increased solar flux exponentially. By mid-month, the object was absorbing significant energy, hundreds of watts per square meter. Still no outgassing, no brightening beyond reflected sunlight, but infrared telescopes detected subtle changes. The thermal emission spectrum broadened slightly, suggesting internal heat redistribution rather than simple surface warming. As October 29th approached, the changes accelerated. Small fluctuations in brightness appeared random at first, then developing periodicity. The thermal profile showed transient hotspots, localized regions warming faster than surroundings, as if internal structures were selectively absorbing solar energy. Then perihelion. The brightness surge, the non-gravitational acceleration, the electromagnetic coupling. For 4 chaotic minutes, 3I Atlas's behavior defied every baseline measurement from previous months. And afterward, the chaos ended, replaced by order. Post-perihelion light curves showed steady brightness maintenance. Thermal regulation kicked in,
temperatures stabilized at levels inconsistent with passive equilibrium. The object's trajectory, though altered, became predictable again, following a smooth path with minimal perturbations. The radio emissions appeared. The magnetic wake formed. The halos developed regular rotation-linked variations. In short, before perihelion dormancy, during chaos, after function. This sequence mirrors technological systems undergoing startup. Consider spacecraft emerging from hibernation mode. Solar panels deploy batteries, charge sensors, activate onboard computers, run diagnostics. There's a transition period, noisy, unpredictable, before systems stabilize into operational states. Dr.
Raj Patel, an aerospace engineer at Caltech, wrote a speculative paper comparing 3I Atlas's timeline to spacecraft boot sequences. He identified phases: energy absorption, charging anomalous behavior, initialization, stabilization, operational mode, sustained low-level activity maintenance. The analogy isn't proof it's pattern recognition, but patterns matter when alternatives fail. The reactivation hypothesis requires addressing fundamental questions. What could remain functional after millions of years? What mechanisms would lie dormant, then activate on solar exposure? And crucially, what purpose would such activation serve? Materials science offers partial answers. Certain substances phase change materials. Glass's supercooled liquids can exist in metastable states indefinitely until energy input triggers transitions. Shape memory alloys, for instance, remain distorted when cold, but snap back to designed shapes when heated. Photochromic compounds change properties under light exposure, then retain those changes until external conditions change again. If 3I Atlas contained materials with similar properties, structures that transition between states, depending on temperature or radiation, perihelion could have triggered cascading transformations. Heat-sensitive latches might release stored mechanical energy. Photoreactive compounds might initiate chemical reactions. Conductive pathways cooled into insulators by deep space cold might restore conductivity when warmed. None of this requires intelligence or intent. It only requires design that anticipates conditions. A system engineered to respond to stellar proximity, even if its creators are long extinct and its purpose forgotten, could still execute embedded routines when circumstances align. Ancient Egyptian djed pillars, symbolic objects representing stability and endurance, were used in rituals believed to awaken latent power. Ceremonies involved raising the djed, an act symbolizing resurrection, reactivation, reconnection with divine energy. Metaphorically, the concept resonates: dormant structures brought back to function through specific actions, returning to purpose after dormancy. Sumerian texts describe them as divine decrees or powers that could be transferred, activated, or lost. They weren't abstract. They were treated as tangible concrete capable of changing state. Whether these concepts reflected deeper ancient knowledge or were purely symbolic, they demonstrate humanity's long recognition that some things can transition between dormancy and activity, between potential and function. 3I Atlas's brightness surge might be understood similarly, a system briefly energized by the sun executing functions embedded in its structure, then settling back into maintenance mode once the intense exposure ended. The luminescence persistence supports this. Weeks after perihelion, the object's light curve remained unusually stable, not fading as rapidly as reflected sunlight alone would predict. If internal processes stored energy during perihelion and released it gradually, this extended glow would be expected. Phosphorescence. The slow release of absorbed light occurs naturally in many minerals, but typical phosphorescence fades within hours. For 3I Atlas to remain subtly luminous for weeks would require extraordinary energy storage, possibly through mechanisms unknown in natural mineralogy. Alternatively, the object might have activated systems that continued drawing power from residual solar energy, stored in batteries, capacitors, or chemical reservoirs? If so, the gradual dimming represents not passive cooling but deliberate power down as stored reserves depleted. One intriguing detail, the 19-hour periodicity, appeared consistently only after perihelion. Before, brightness variations were irregular, chaotic. Afterward, they became rhythmic, predictable. This suggests something about the object's rotation or surface orientation changed, either physical restructuring or activation of features that modulate light in regular patterns. Consider a spacecraft tumbling randomly through space until solar exposure charges its batteries and powers attitude control systems. Those systems fire thrusters or spin gyroscopes, stabilizing rotation into a controlled spin. From Earth, we'd observe the transition from chaotic light variations to periodic pulsing as the spacecraft established stable orientation. 3i Atlas's transition from irregular to regular brightness variations matches that scenario uncomfortably well. The reactivation hypothesis faces substantial criticism. Skeptics argue it anthropomorphizes the object, projecting human technological concepts onto natural phenomena. They note that without direct evidence, resolved imaging showing surface changes or spectroscopy detecting activation by products, the hypothesis remains speculation. Fair point, but the alternative that all observed transitions, timing, and patterns arose coincidentally from unrelated natural processes accumulates improbabilities rapidly. By early December, as 3i Atlas faded from telescope range, the debate had settled into uneasy truce. Mainstream publications avoided the reactivation terminology, preferring perihelion-induced state transition or thermal activation of embedded structures. But in private conversations, at conference dinners, in late-night emails, researchers admitted the elephant in the room: the timeline and behavior looked purposeful. Whether that purpose was conscious, programmed, or emergent from complex material interactions remains the central question. But purpose in some form seemed increasingly difficult to deny. By mid-November, 3rd Atlas had traveled beyond Mars's orbit, receding into the outer solar system at nearly 50 kilometers per second relative to the Sun. The intense scrutiny of perihelion was over. Telescope time became scarce as the object dimmed toward magnitude 1920, then fainter still. Soon, only the largest instruments could track it, and only briefly. Yet even in departure, anomalies persisted. The trajectory showed sustained, non-gravitational acceleration, subtle but measurable, continuing long after any conventional outgassing should have ceased. More perplexing, the acceleration vector wasn't purely radial from the Sun. It tilted, angling several degrees out of the ecliptic plane, steering the object toward higher galactic latitudes. Dr. Jane Morrison, an orbital dynamics specialist at JPL, modeled the departure trajectory using every available measurement. Her analysis revealed that 3i Atlas wasn't simply fleeing the Sun along its incoming vector. It was adjusting course, deviating from the pure hyperbolic path that gravity alone would dictate. The deviation was small, mere fractions of a degree, but over time that tiny angle would translate to enormous distances. Extrapolating forward, by the time 3i Atlas re-entered interstellar space, beyond Neptune's orbit, it would be tens of millions of kilometers off the path predicted by gravity alone. Such deviations occur naturally when comets outgas asymmetrically. But again, 3i Atlas showed no gas emissions, no visible jets, no activity suggesting ongoing mass loss that could produce thrust. The only remaining explanations: either the object possessed residual volatiles, venting, invisibly possible but unsupported by spectroscopy, or something about its interaction with the solar wind or interplanetary magnetic field continued to generate small forces. Or the third option no one wanted to say aloud: it was steering. The light curve added to the mystery. As 3I Atlas receded, its brightness should have diminished predictably following the inverse square law of distance. For the first 2 weeks after perihelion, it did almost. But by late November, the dimming plateaued. Despite increasing distance, the object's magnitude held constant within narrow ranges for several days before resuming decline. This behavior suggested either changing orientation, presenting more reflective area to compensate for distance, or continued faint emissions supplementing reflected sunlight. Either way, it implied ongoing activity, passive or active, that violated expectations of inert debris coasting into oblivion. By late November, radio telescopes could no longer detect emissions. The faint hiss that appeared around 812 milliamperes immediately after perihelion faded below noise thresholds. If signals were still present, they were too weak or too intermittent for current instruments to isolate. Optical imaging captured one final detail: the halo. The faint asymmetric glow surrounding 3I Atlas, detected in infrared and faintly invisible wavelengths, dimmed gradually, but remained detectable longer than thermal models predicted. As of December 1st, when the last confirmed observations were recorded, the halo persisted, a ghostly aura surrounding the fading point of light. Ancient departure myths resonate across cultures. Quetzalcoatl, the Mesoamerican feathered serpent deity, was said to have departed on a raft across the eastern sea, promising return in future ages. Sumerian texts describe gods ascending to the heavens, traveling in barks or boats that crossed celestial rivers. Hindu cosmology speaks of vimanas, flying vehicles ascending into the stars. These myths aren't evidence of anything beyond human imagination, but they reflect a deep-seated intuition that the cosmos is traversed, that journeys occur across incomprehensible distances, and that departures are never truly final because the universe is cyclic, interconnected. 3I Atlas's departure carries that mythic weight intentionally or not. It arrived from beyond, passed briefly through our space, interacted with our sun, then departed, not destroyed, not captured, but continuing its journey, altered by the encounter in ways we measured, but don't fully understand. Where is it going? The trajectory projected forward doesn't point toward any particular star. The object emerged from the direction of Ursa Major and will depart toward the constellation Hydra, eventually escaping the sun's influence entirely and returning to the interstellar medium. Over thousands of years, its path will carry it past distant stars.
Over millions of years, galactic dynamics, gravitational perturbations from massive star clusters, interactions with molecular clouds will reshape its orbit unpredictably. We cannot forecast its fate beyond a few centuries. Perhaps it will eventually encounter another star system repeating the perihelion dance, with a different sun observed by different astronomers or left unobserved if no watchers exist there. Perhaps it will collide with another object, shattering into fragments scattered across parsecs. Perhaps it will drift indefinitely, a solitary relic in the vast dark, its brief illumination by our sun merely one flicker in an unending night. Or perhaps, as some dare speculate, Atlas will eventually reach a destination, a region of space, a structure, an origin point where its journey began or where it's programmed to return, carrying data samples or memories, encoded in structures too subtle for us to detect.
The International Astronomical Union officially classified 3I Atlas as an anomalous interstellar object, a designation that acknowledges its strangeness without committing to explanations. The Minor Planet Center lists it as hyperbolic trajectory, confirmed non-gravitational forces detected, classification pending. Pending. That word encapsulates everything. Uncertainty, caution, the admission that our categories don't fit. By December 5th, 3 Atlas had faded beyond magnitude, 21 effectively invisible to all but the world's largest telescopes under perfect conditions. A final campaign using the European Extremely Large Telescope attempted observations but captured only noise. The object had slipped into darkness, and yet its passage left marks,
data sets that don't reconcile models that require extraordinary parameters, observations that suggest more than we're ready to conclude. Several teams have submitted proposals for long-term monitoring.
If space-based telescopes with sufficient sensitivity eventually track 3I Atlas decades hence, we might learn whether its trajectory continues evolving or stabilizes into a clean, hyperbolic escape. But practically, the object is gone beyond reach, beyond measurement, beyond our ability to interrogate further. We're left with memories recorded in terabytes of data, thousands of images, hundreds of spectra, and countless hours of scientific debate. And one undeniable truth: something came from interstellar space, behaved unlike anything we'd seen, and departed carrying mysteries we may never solve. 3. Atlas doesn't provide answers. It provides a test, a challenge to frameworks we've built over centuries of scientific observation and philosophical contemplation. How we respond to that challenge reveals more about humanity than about the object itself. Let's begin with categories. We divided the universe into natural and artificial, assuming clear boundaries. Stars form naturally through gravitational collapse. Spacecraft are built deliberately through engineering. One category is cosmic universal inevitable, given sufficient time and matter. The other is contingent rare, dependent on intelligence. 3I Atlas sits uncomfortably between. Its properties align more with artifacts than with natural bodies, yet no intelligence has claimed it, no transmission emanated from it, no function is obvious. Either our categories are inadequate or something exists beyond binary classification phenomena that possess structure and order without consciousness, design without designers, purpose without intent. Possibility 1. Unknown. Physics. Perhaps matter and energy interact in ways we haven't discovered, producing organized structures that mimic design through natural processes occurring at scales or time scales we've never observed. Just as crystals grow into intricate patterns following chemical rules, perhaps larger-scale assemblies form in interstellar space, shaped by radiation pressure, magnetic fields, and cosmic rays into configurations that appear optimized. This explanation preserves naturalism, the philosophy that everything arises from physical law without teleology or intervention. It demands humility, acknowledging that our understanding of physics, though vast, remains incomplete. But it requires inventing new physics specifically to explain 3I Atlas. That's not inherently wrong. Science progresses by discovering new phenomena, but it becomes increasingly contrived when each observation demands another ad hoc mechanism. Possibility 2. Ancient technology. Somewhere in the Milky Way's 13 billion-year history, technological civilizations arose, built things, and either left behind relics, intentionally probes, markers, seeds, or unintentionally debris fragments, wreckage. 3I Atlas might be such a relic, ancient beyond comprehension, its original function lost, its creators extinct or irrelevant. This explanation requires one extraordinary assumption: that intelligence exists or existed elsewhere. But it requires no new physics, no unknown materials, no exotic processes, only technologies we can imagine or have already developed ourselves. Solar sails, magnetic shielding, thermal regulation. These aren't science fiction. They're engineering problems we've already solved or are actively pursuing. The parsimony debate hinges on which assumption feels larger: unknown. Natural processes tailored to fit observations, or extraterrestrial technology consistent with observations. Possibility 3. Emergent complexity. Perhaps the universe, given enough time and variation, explores every configuration space, every possible arrangement of matter and energy. Most configurations are chaotic, ephemeral,
but occasionally, purely by chance, structures emerge that possess coherence, stability, function. Not designed, but selected through something resembling natural selection at cosmological scales. In this view, 3i Atlas might be a rare accident, a statistical anomaly where matter organized itself into configurations that happen to look purposeful. Like the Cairns-Smith hypothesis for life's origin, clay crystals, spontaneously developing informational patterns that eventually gave rise to biology. Perhaps structures form in interstellar space that approximate technology without ever being built. This is appealing philosophically because it dissolves the natural-artificial dichotomy entirely. Everything is natural. Some things just look artificial because human brains evolved to detect patterns and infer agency. But this also requires extraordinary faith in chance, that randomness, given enough iterations, produces structure indistinguishable from design.
The Drake equation, formulated in 1961, estimates the number of active communicative civilizations in our galaxy by multiplying probabilities. Star formation rates, planet occurrence, abiogenesis, intelligence development, technological longevity. The result is famously uncertain, ranging from "we're alone" to "millions exist." 3i Atlas modifies that equation. It suggests that even if communicative civilizations are rare evidence of past civilizations, might be abundant scattered through the galaxy as debris fragments, relics. These artifacts don't transmit signals, they don't seek contact. They simply drift, occasionally passing through stellar systems where younger species notice them and wonder. This resolves part of the Fermi paradox. Where is everybody? Perhaps they're nowhere because they've gone extinct, but everywhere because they left traces. Another implication: detectability. We've searched for extraterrestrial intelligence primarily through radio signals, deliberate transmissions from active civilizations trying to communicate. But 3i Atlas suggests a different search strategy. Look for anomalies, objects that don't fit natural templates, orbital trajectories that suggest steering, brightness variations that indicate structure. This approach, sometimes called the techno-signature search, doesn't require extraterrestrials to want contact. It only requires them to have existed and built things that eventually drift into our observational range. Göbekli Tepe, an archaeological site in Turkey, dates to approximately 9600 BCE, predating agriculture, predating settled civilization as we understood it. Massive stone pillars arranged in circles carved with intricate symbols, constructed by hunter-gatherer societies, millennia before writing cities or metal tools. For decades, archaeologists assumed such structures could only be built by agricultural societies with surplus labor and centralized organization. Göbekli Tepe shattered that assumption, proving that complexity can arise earlier, stranger, more sophisticated than models predicted. 3i Atlas might be our cosmic Göbekli Tepe, evidence that the universe contains surprises we're not intellectually prepared for, phenomena that challenge foundational assumptions about what's possible, when, and how. The emotional response matters too. Some react to 3i Atlas with excitement, the possibility of discovering we're not alone, that intelligence has flourished elsewhere, that relics of those civilizations drift among the stars. Others respond with unease, the destabilization of humanity's assumed centrality. The discomfort of mysteries that resist answers the existential weight of insignificance. And some feel sadness. If 3i Atlas is artificial, it represents a civilization that arose, peaked, created, and vanished, leaving behind only silent fragments. It's a memorial without a grave, a testament to impermanence, a reminder that everything eventually ends. Perhaps the deepest implication is epistemological. 3i Atlas forces us to confront the limits of knowledge. We measured it, tracked it, analyzed it with humanity's most sophisticated instruments. And still, we don't know what it was. That limitation isn't temporary, fixable with better telescopes or more funding. It's fundamental. Some things are knowable only by proximity, by interaction, by direct examination, impossible across millions of kilometers and light years of separation. We're left with probabilities, correlations, models that fit but don't prove. That's not failure, it's honesty. Science doesn't always provide definitive answers. Sometimes it provides better questions. And the question 3i Atlas leaves us: what else is out there drifting unseen, unnoticed, unrecognized? And what does our universe look like if we admit we've been surrounded by evidence all along but lacked the frameworks to see it? As December's cold nights settle in and 3i Atlas fades beyond our instrument's reach, we're left with something more valuable than answers: the humility of uncertainty and the privilege of having witnessed something extraordinary. Let's revisit what we know confirmed by observation and measurement. 3i Atlas arrived from interstellar space on a hyperbolic trajectory with eccentricity 6.137. Its closest approach to the Sun occurred October 29, 2025 at 1:36 AU. During perihelion, it exhibited non-gravitational acceleration measuring approximately 3.5 x 10^5 A brightness surge coincided with solar flare activity from region AR 3510. Surface temperatures remained anomalously low throughout solar encounter. Below 190 Kelvin spectral analysis revealed narrow emission features at 470 and 520 nanometers spaced in 2 ratio. Thermal regulation demonstrated zero inertia, responding instantaneously to solar flux variations. The dust tail exhibited inverted curvature pointing partially toward, rather than away from the Sun. Multiple observatories recorded incompatible data regarding position, brightness, and spectral characteristics. Radio emissions around 412 MHz were detected by some instruments, but not others. The object's wake persisted in the solar wind for over 12 hours, showing organized structure post-perihelion trajectory, showed continued non-gravitational forces and oblique steering out of the ecliptic plane. Its light curve remained stable far longer than passive reflection allows. These aren't speculation. They're measurements captured by instruments designed to detect photons and particles, with exquisite precision analyzed by scientists whose careers depend on accuracy and skepticism. That 3i Atlas's surface may contain metallic or engineered composites, that its behavior suggests reactivation near the Sun, transitioning from dormancy to function, that electromagnetic coupling with solar magnetic fields produced the observed accelerations, that the object's structure may be compartmentalized with distinct regions serving different functions, that ancient civilizations might have created objects like this, either deliberately as probes or accidentally as debris, that what we witnessed was not random interaction but coordinated response. These remain hypotheses because we lack direct evidence, resolved images showing surface structure, spectroscopy proving artificial chemistry, or unambiguous signals demonstrating intent. The scientific method demands withholding conclusions until evidence compels them. What remains unexplained? Why the object's behavior synchronized perfectly with solar activity? The flare, the brightness surge, the acceleration within minutes of perihelion. When the probability of such coincidence approaches negligibility, how it regulated temperature without volatiles, without obvious heat management mechanisms, responding faster than thermal conduction through natural materials allows. Why 3 major space agencies recorded fundamentally incompatible observations of the same object at the same times, suggesting anisotropic properties inconsistent with natural bodies. What produced the electromagnetic wake, the radio emissions, the magnetic coupling, all phenomena requiring conductivities and field strengths, orders of magnitude beyond any known natural solar system object. Where the energy came from to sustain post-perihelion activity, luminescence, persisting, weeks, trajectory adjustments, continuing indefinitely, structures organized in ways that don't arise from passive dispersion. These aren't minor puzzles solvable with slightly better instruments. They're foundational contradictions between what we observed and what natural models allow. Tonight, as 3i Atlas slips beyond the edge of detectability, it carries with it a possibility we cannot quantify. Perhaps in the 13.8 billion years since the universe began, intelligence has arisen countless times, some flourishing briefly, others persisting for eons. Some built monuments, others sent messages, and perhaps some long ago sent simple structures outward into the dark. Not to conquer, not even to communicate, because by the time such objects reach distant stars, their creators might be extinct, their civilizations dust, their languages meaningless noise. But simply to endure, to move through the galaxy as witness, as memory, as proof that something once existed, looked upward, wondered, and built. What if 3i Atlas was exactly that? A fragment of ancient purpose, neither alive nor dead, but something between. A relic that remembers through structure and material how to respond when starlight warms it, how to adjust when magnetic fields pulse through it, how to maintain itself against entropy using principles embedded in layers we cannot resolve with our telescopes. And if one such object passed through our system noticed, because it came close enough to the sun to activate, to respond, to leave traces, we could measure how many others have passed unnoticed, slipping through the outer reaches of the Oort cloud, never entering the inner solar system, never approaching close enough to trigger whatever dormancy breaking threshold exists within their ancient designs. What if the galaxy is full of these silent travelers, fragments of civilizations whose names we'll never learn, whose purposes we'll never decipher, whose origins recede into timescales that dwarf the age of Earth itself? What if we've been surrounded by evidence all along but mistook it for asteroids, comets, debris, background noise, in a cosmos we assumed was mostly empty? And one more question hangs there suspended in the cold space where 3i Atlas now travels. Was this object merely passing through our star's light, absorbing energy, as any passive material would, reflecting and emitting, according to physics we'll eventually understand? Or was it doing what it was built to do, sampling our sun's spectrum, measuring our system's properties, recording data in formats we can't recognize, executing protocols laid down millions of years ago by creators who knew that someday somewhere their work might encounter stars, planets, and perhaps even witnesses capable of noticing that something passed through that wasn't quite like everything else? And if it was, leaving us a message written in mathematics of material response, encoded in the precision of its trajectory, spelled out in the synchronized timing of flare and acceleration and brightness. Are we wise enough yet to read it, or will we file this encounter as anomalous, unexplained, pending further study, and move on, missing the first words of a conversation we didn't realize had begun? Before you sleep tonight, consider this. Every photon that reached our telescopes from 3i Atlas traveled across space, carrying information about composition, temperature, motion, structure. We captured those photons, recorded their testimony, and now possess more data about this object than about most asteroids in our own solar system. Yet we remain uncertain. That uncertainty isn't weakness. It's honesty. It's the acknowledgement that the universe is larger, stranger, and more sophisticated than our models currently encompass. 3i Atlas has departed, but the questions it carried to us remain. And until we build better instruments, develop deeper theories, or perhaps encounter another visitor willing to make its nature clearer, those questions will linger in the space between what we measured and what we understand. The universe, it seems, has been speaking for billions of years. Perhaps it's time we learn to listen. Stay curious, keep watching the sky, support the telescopes and missions that make observations like this possible. And remember, every point of light moving against the stars carries a story. Most are ordinary rocks, ice, ancient debris following gravitational choreography billions of years old. But some rare, precious, extraordinary carry something more. and we have the privilege, the tools, and the responsibility to notice them, measure them, and admit when they defy explanation. Because the next 3i Atlas is already out there moving through the dark, approaching some star system, maybe ours again, decades or centuries hence, and whether we recognize it depends entirely on whether we've learned to see what we're looking at. Sleep well. The universe is vast, ancient, and full of quiet wonders waiting to be noticed.